G'day viewers. In this segment I'll talk to you about congestion and the topics we're going to cover to control it. So we're still in the transport layer, having a little more fun. We've talked about reliability in the transport layer, and now it's time to cover congestion control, which is another major component of it. And we'll also find that this is a topic that's not confined to the transport layer. We'll go back and talk a little bit about how the network layer affects congestion as well. So congestion is like a traffic jam that occurs inside the network. In this segment, I'm mostly going to talk to you about what congestion is and where it comes from. And I'll then briefly mention some of the topics that we're going to cover as we develop mechanisms that control congestion inside networks and prevent it from occurring. So here's an earlier slide so you can just recall what goes on inside routers and switches. Routers and switches have some amount of internal buffering for contention when multiple input packets want to go to the same output. So in this diagram I have a switch in the middle here, or a router. I have the inputs on the left and the outputs on the right. There's buffering inside the router because, for instance, I might at a particular moment in time want to send traffic from 3 different inputs to a single output. Well, in that case, not all of the packets can go on the output line at the same time. Since they've come into the switch on the input line, then they need to be stored somewhere inside the switch. And this is just temporarily until they can go outside the output line. In this picture, there's a simplified view of the internal structure of routers that will be sufficient for our purposes. We can just imagine it as though every output line, every output port has its own queue. So you can see here there are 3 different queues inside the router by the output ports to handle traffic. And as traffic comes in from the input, it goes to the right output and it may be queued. Here are packets queued inside these queues, just because we might have gotten more packets from the input than we could send out the output immediately. And you can see mostly these queues are empty, except for one of them is getting kind of full, and that queue, that output link, is becoming congested. Most of these queues, they could be run in different ways, but the typical implementation of a queue, which we'll consider to be the case unless I say otherwise, is a FIFO queue, or a first in, first out queue. That simply means that as packets or segments come in, they're placed in the queue in the order they come in, and they're sent out such that the first one in the queue is the first one out. And when this queue is full, new packets can't fit in, so they're discarded. So you can see here that the buffering inside routers is actually beneficial. It's there to provide queuing to absorb these short-term bursts, just when 3 input ports wanted to send to the same output port at the same amount of time. So it's beneficial. The routers wouldn't work without them. On the other hand, you should also be able to see that if there is a sustained overload or a long period when the input rate is persistently bigger than the output rate, then those queues will fill. There's nothing else they can do. And when they fill, they will overflow and we will begin to lose packets inside routers. This is congestion. This is how congestion occurs. Now, it's also the case that there's no getting rid of congestion. You might imagine if we just made every link have the same capacity, then everything would be fine. There'd be sort of no mismatches. But congestion is a function of the traffic patterns, because I keep using the example of 3 input ports sending to the same output port. Even if all of the links have the same speed, we'll still need some buffering in routers. You'll also have buffering if, for example, the input ports are faster than the output ports. So you might have 3 packets arrive rapidly, and if they're going at a slow link, we'll also need buffering for that case. Well, that's congestion, but let's think a bit about what happens when it occurs. What is its effect on performance? And this can help us understand why it's actually bad. We know there's a little loss. So let's go through this. I'll go through both the graphs on the left and the right. On the left-hand side, we're looking at the effect of on good put as we increase the load on the network. Good put is simply the amount of traffic, desired traffic, that gets through the network. You could think of it as almost synonymous with throughput. So the x-axis here is offered load. As the offered load increases, what would we like to happen to the good put or throughput through the network? Ideally, it should rise exactly with the offered load. As that goes up, we expect the throughput of the network to go up. And of course, when the offered load reaches the capacity, the highest amount of data that could go through the network, then we would expect that even if you offer more load, the throughput can't go up any further. This is an ideal curve, but really the traffic is statistical. It's not very smooth. There are fluctuations. Sometimes we will have queues that overflow. And in that case, the more realistic curve is something like this. So this one was ideal. This is desired. In that there's a slight degradation. You can see there's a bit of a gap here, and in that the performance is falling off a little bit as the load increases. That's because some number of packets are lost as there are fluctuations and some of the queues overflow. As we increase the load to close to the capacity, it gets more likely that we'll lose more packets. So the gap here is growing. On the other hand, what can happen with congestion, and this is where congestion is really bad, is our throughput can go like this, or our goodput, can go like this. This is congestion collapse. Now it can be, and this is why I've shown goodput on the axis here rather than throughput. Goodput is desired traffic that comes through the network. So if you have retransmissions of the same packet through the network 7 times, you only get it to count once as useful information going through the network. In the collapse scenario, because packets are lost, we're retransmitting them. And it's possible, if the protocols don't work very well, if they're not designed for very high levels of load, for us to end up retransmitting packets lots of times and having them lost many times, so that even though we're sending a lot of packets, less useful information is getting through the network, and the network is in a state of collapse. This, in fact, is something that happened in the internet in the early days. So we need to be careful as we're entering congestion here, and as we go up to very high levels of load, bad things can happen inside the network. What about for delay? That's another really measure of performance of the network. Okay, here's the offered load of 1, the maximum. Now, the ideal delay would be something like this. That is, it would be a constant low value that's really the propagation delay across the network. You can't do better than that. However, what we find is that as the load gets closer and closer to the capacity, there's more queuing statistically, and that's going to increase the delay. Initially, and until we get close to the offered load, we will have output rates that are greater than the input rates, and so we would expect there to be almost no queuing. In that case, the delay is really not going to go up much at all. However, as we get close to congestion, those queues are going to start to build. And as they start to build, the delay will build. And as we get very close to the capacity, those queues will be full nearly all of the time, and our delay will go up and up. So our delay goes something like this. Actually, in theoretical models where there's no limit on the router buffer size, they can go right up to infinity as your offered load reaches the capacity. The point is that as we approach congestion, the delay starts to climb up. So here's a cleaned up version of this picture. And you can see that operating the network in a congested state is not good. That's what I would like you to take away. We begin to lose packets, so we have to retransmit more. And we're also adding delay to the packets through the network. So we're not getting any more useful information through, and we're having to spend a longer amount of time to send it through the network. It's a lose. Here's the slide just to summarize some of those effects. Congestion occurs as the offered load rises and those queues start to fill. And it's bad. Delay and loss rise. They can both begin to rise sharply as we get close to the capacity, as the offered load gets close to the capacity. Throughput can also fall because of this loss, and goodput can fall even more if we're sending retransmissions many times, just trying to get packets through the network. This is all bad. So we would like to operate the network before we get to a congested state. We still want to be able to use all of the capacity of the network, so it's a bit of a dance to try and do this, to use all of the capacity yet not congest the network. Okay, so I've actually been talking so far mostly about congestion. That's a problem. The task we're really trying to accomplish, however, is not so much to deal with congestion as to allocate bandwidth. The network has different bandwidth resources inside it on the links, and really its whole purpose, its whole reason for being, is to allocate this bandwidth to different senders to allow them to communicate with receivers. So the problem for the network is one of bandwidth allocation. A good bandwidth allocation should be efficient and fair, and this is going to capture our notion of congestion. An efficient allocation means that we're getting to use most of the capacity in the network. Those links are not idle, we're getting to use them. However, we're not running the network in such a way that there's congestion and a lot of queuing, because we've just seen the bad effects that occur because of that. A fair allocation is one in which every sender who wants to use the network gets some reasonable share of the network. So no one is precluded from using the network. We sort of add this as a secondary condition because you don't want to be efficient simply by choking senders which are problematic for congestion. Now, I'm going to talk just a bit about the bandwidth allocation problem in general now. We'll see solutions to it in the coming lectures. But I'd like to make a few general points for you to remember about it and keep in the back of your mind, because they're important for the solution. One key observation I want to make is this, that to allocate bandwidth effectively, both the transport and the network layer need to work together. That's interesting, isn't it? Because previously many of our mechanisms have been confined to a single layer. Here we need two. Why? Well, we need the network layer because we've seen congestion is something that manifests itself inside routers. That's the domain of the network layer. So only the network layer can directly see congestion and tell someone that it's occurring. On the other hand, the transport layer is the layer that is really injecting the traffic into the network on behalf of applications. It's the layer that's causing the congestion by offering the load. So it's the only layer that can really control this congestion by controlling the offered load. So they're both going to play a part. You might also wonder why this is hard to solve the bandwidth allocation problem. After all, it seems like if you just have a link of a certain value and senders want to use it, we could simply divide the bandwidth and call it quits. Well, it's a little harder than that for several reasons here. Now, the actual number of senders and how much traffic they're sending and even where they're sending to is something which is constantly changing over time as people surf different web pages, go and get a coffee, watch a movie, go out, and so forth. So the workload of the network is something which is always moving around. We don't have any static picture to divide it. What's more, there's no single pie to divide. Different senders, depending where they're sending, can have a shortage of capacity in different places in the network. Where those places are is going to depend where they're sending to, so it's something that can move around too. And not only that, but like our routing formulation, where no one had an overall view of the network, the same case holds here. There's no single party who can see the whole network and look at all of the traffic information and say, here's what we should do. So everyone is just going to have to work based on their partial knowledge of the network. This is a distributed system problem once again. You can see this is quite an interesting and challenging problem. That's what makes congestion such a fascinating topic to study. Okay, so we still haven't got to the solution. It's going to take us many lectures to go over how TCP solves the bandwidth allocation problem. But I do want to give you just a little bit of context for the solutions we'll look at. Much like the routing problem, this is going to be one in which we come up with solutions in which all of the different hosts instead of routers this time, who are sending traffic into the network are going to need to adapt their load on the network based on their own view of the network. So all of the senders are operating independently and concurrently. Nonetheless, we want to design the way they operate and adapt their load such that the network as a whole arrives at an efficient and fair allocation when you sum up all of the independent actions of these senders. And since the offered load on the network is something that's changing all of the time, this adaptation is never actually going to end. We would like it to quickly converge to a good operating point that's fair and efficient, but as the traffic on the network changes, the bandwidth allocation is also going to change over time. Okay, so I've now told you about congestion and framed the problem. So we've covered the nature of congestion here. In the coming segments, we're going to go over a little bit more about what we're looking for in a solution to the bandwidth allocation problem. And then we're going to see different kinds of mechanisms we can use to solve the problem. AIMD is something which will come up as a desirable kind of operating point for allocating bandwidth. And then all of these other topics really have to do with how TCP comes up with a solution to the bandwidth allocation problem. It's a crucial part of its function. Okay, let's see how it all works.